Hi, and welcome back. Today, we are looking at the binary number system. So we will mainly dwell on the conversions from binary to decimal, binary to decimal, decimal to binary, binary to octal, decimal to octal, etc. So by the end of this lecture, I should be able to describe the binary number system, convert a number from binary to decimal and vice versa, decimal to octal and vice versa, octal to binary and vice versa. So in the previous lecture, we looked at the decimal number system, where we say this is a number system that has 10 symbols, which represent the digits in that number system. And these symbols are 0, 1, 2, 3, up to 9. We also performed some arithmetic operations in that number system, that is addition, subtraction, multiplication, and division. So in this lecture, we are going to focus on the binary number system. The binary number system, this is a positional numeration system to the base 2. Unlike the decimal one, which is base 10, this one is base 2. Remember, dec, that's the prefix for 10, and by is the prefix for 2. So the digits that are in the binary number system are called bits, which is the short for binary digit. And those ones are 0 and 1 only. So any binary number can therefore be expressed, or is therefore expressed as a sequence of zeros and ones, possibly with an embedded binary point. So the binary numbers with no fractional part are called binary integers. Right. Now let's look at the binary to decimal conversion. Right. We saw that in the previous lecture, that we can convert a decimal number, or we can express a decimal number in its expanded notation. We can also do the same in the binary number system. The concept of place values still remains the same. So here we have, let's take an example. Here we have the number 10. The place value of this 0 is 2 to the power of 0. And the place value of this 1 is 2 to the power of 1. So to get the expanded notation of this number, we are going to multiply each bit by its place value. So this is going to be 1 times 2 to the power of 1 plus 0 times 2 to the power of 0. Now let's look at another one. Let's suppose we want to express this one, this binary number, in its expanded form. The place values starting from the right to the left. This one will be 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and 2 to the power of 5. Take note that we are just saying this one is place 0, place 1, place 2, place 3, place 4, and place 5. So what you now do is we multiply each bit by its place value. So the first one will be 1 times 2 to the power of 5 plus 1 times 2 to the power of 4 plus 0 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 1 times 2 to the power of 0. 2 to the power of 0 is 1. That's why here we have 1 times 1. And 2 to the power of 1 is 2. That's why here we have 0 times 2. Right. Now let's look at another example that is a binary point, this one. If we have a binary point, remember from the binary point going to the left, our place values will start from 0, 1, 2, 3, etc. And from the binary point going to the right, our place values will start from -1, -2, -3, etc. So it means expressing this one in its expanded form will give us, right, we are multiplying this number by 2 to the power of 2, because the place value of this one is 2. Remember, this is 0, 1, 2. So that's 1 times 2 to the power of 2 plus 0 times 2 to the power of 1, which is the same as saying 0 by 2 if you want, and then plus 1 times 2 to the power of 0, which is the same as saying 1 times 1, plus this. Now remember, we said this position of this one is -1, so that would be 1 times 2 to the power of -1, 1 times 2 to the power of -2, 0 times 2 to the power of -3, and 1 times 2 to the power of -4. So this will give you the expanded notation for this one. Right. Now, if you have understood the concept of expanded notation, converting a number from binary to decimal becomes very simple, because what you just have to do now is, if you want to find out what decimal number is equivalent to this binary number, you just have to simplify this expression. you simplify it, you add the numbers, and then that will give you the decimal equivalence of that number. So for instance, this number 10, if we simplify 1 times 2 to the power of 1, this will give you 2 plus 0 times whatever, that's a 0. So that means 10 in binary is equivalent to 2 in decimal. You can simplify this part to get the equivalence of this number in decimal, etc. Right. Moving on. Sometimes a subscript 2 is used to distinguish the numbers because it may not be immediately clear whether this number is decimal, is it binary, etc. For instance, if you just see the number 1011, you don't know whether this is a decimal number, which is 1011, or maybe it's a binary number, which is something else. So we can use the subscript 2 to denote that this is a binary number and not a decimal number. If this subscript is not used to denote, sometimes you can get the phrase like, consider the following binary number. The moment you see the phrase binary number, it means it's base 2. So for ease of reading, binary numbers can be separated into 4 bits, into 4-bit groups to the left and right of the binary point. By binary point, we mean this dot here. In the decimal number systems, we say this is a decimal point. But because this is a binary number system, we say this is a binary point. So given a number like this one, we can rewrite it by grouping the bits in groups of 4 so that it becomes easier to read. It doesn't change anything. So starting from the binary point going to the left, we'll group our bits in 4s. So that means we are going to say these first 4 bits, right, they are the bits that we have here. And then we have these next 4 bits, they are the bits that we have here. What we've just done is to insert space in between them so that it becomes easier to read them. Now, starting from the decimal point again, going to the right, we again group them in groups of 4. So we take these 4 bits and we have them here. Then we insert space and we take the next 4 bits. If we no longer have enough bits, we just take the remaining bits. So in this case, we only have 3 remaining bits, and then we have them grouped together like this one. So this is only done to make sure that the numbers are easier to read. But take note that you cannot just start grouping them from anyhow. Like you cannot just say, okay, I want to group them from the right after this decimal, after this binary point. And then you say, I want to group them as 1 0 1 0 and then 0 1 1. We group them starting from the binary point going to the left and starting from the binary point going to the right. Okay. Now let's take an example of converting a number from binary to decimal. Right. Like we saw previously, we have our number here 1001. This is in base 2. We write it here 1001, and then we write the place values here. Right. This is place value 0, 1, 2, 3. So this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. Right. Now we know that these place values that we have here, we are going to multiply them by the bits that we have here. And because we only have zeros and ones, whatever number we have, if we multiply it by 0, it's still going to give us a 0. So we are going to ignore those bits that have zeros, and we focus on those ones that have 1. So we say 2 to the power of 1 will give us 1, and we multiply it by the bit 1, we get 1. Then we have our 1 here. We are going to discard these ones because whatever their values, if we multiply them by 0, we'll still get zeros. So we come here, 2 to the power of 8, 2 to the power of 3, that's 8, multiplied by 1 will give us 8, and then we have our 8 here. We now add these numbers, 1 plus 8, and we get 9. So it means the decimal number 1001 is, the binary number 1001 is equivalent to the decimal number 9. That's how you do the conversion. So to check if you have understood these concepts, I want you to do this activity. Convert these numbers given here. Right. Now we can also convert a number from decimal to binary. And to do that, we just get our number, we perform repetitive or successive divisions of the quotient by 2, and then we take the remainders from the bottom upwards. Now, for instance, let's take the number 15. Let's suppose we want to convert 15, which is in base 10, to a binary number. What you just have to do is we perform repeated divisions for our quotient. Now, so we start with 15, we divide it by 2. The answer that we get there is 7, remainder 1. So we write 7 under quotients and then 1 under remainders. Then we take 7, which is this quotient here. Right. We are multiplying this. We are now dividing this 7 by 2. 7 divided by 2 will give you 3, remainder 1. And then next, we are now dividing this 3 by 2. 3 divided by 2 will give you 1, remainder 1. And next, we divide this 1 by 2. 1 divided by 2 will give you 0, remainder 1. The moment your quotient becomes 0, it means you are done dividing. And what you do next now is to take your remainder starting from the bottom going upwards, and then we have 1, 1, 1, 1 as our decimal number. So 15 to the base 10 is equal to quad 1 to the base 2. That's how you do the conversion, as simple as that. Then let's look at another example. Let's suppose we want to convert the number 109, which is in base 10, to its binary equivalence. We perform repeated divisions like we just did. We start with the 109, we divide it by 2, we get 54, remainder 1. Next, we are now dividing 54 by 2, we get 27, remainder 0. Next, we divide 27 by 2, we get 13, remainder 1. Next, we divide 13 by 2, we get 6, remainder 1. Next, we divide 6 by 2, we get 3, remainder 0. Next, we divide 3 by 2, we get 1, remainder 1. Next, we divide 1 by 2, we get 0, remainder 1. And we now take these numbers from the bottom going up. So that means 109 to base 10 is now equivalent to 1101101 to base 2. So that's 1101101 to base 2. That's how you do the conversion for integer decimal numbers to binary numbers. Then moving on, let's now look at how do we convert a decimal fraction to a binary number. Now, with the integer decimals, we were repeatedly dividing. With the decimal fractions, we will repeatedly multiply. So we'll be repeatedly multiplying by 2. Right. So and then we'll be taking note of the integral part. So what we do is, for instance, let's suppose we want to convert this number 0.78125, which is in base 10, and we want to convert it to base 2. What we do is we multiply that number, 0.1 by 2, and the answer will be this one. Now, on this answer, the integer is 1. So we take note of the integral part, which is 1. Now, having taken note of that integral part, next, we are now going to multiply the fractional part by 2 again. This fractional part, so this fractional part is 0.5625. We take it down here. We multiply it by 2. We get the answer, and then we note the integral part again. The integral part here is 1, so we bring it here. Now, the fractional part is 0.1250. So we multiply it here by 2, and that will give us 0.250. The integral part here is 0, so we note it here. Next, we take the fractional part of this one, we multiply it by 2, so that will be 0.25 multiplied by 2, we get 0.5. The integral part is 0, we note it here. Next, we multiply 0.5 by 2, we get 1, the integral part is 1, and we see that the remainder now, or the fractional part, is now 0. So we stop the multiplications. And unlike what we did in the previous one, where we were taking the remainders from bottom to top, in this one, where we are doing the repeated multiplications, we will take the integral part from top to bottom. So that means 0.78125 will be equivalent to 11001 to the base 2. Okay. Now, we can also convert a decimal number to an octal number. An octal number is basically a number that is to the base 8. Okay. So what it means is, in the octal number system, we have 8 digits, 0, 1, 2, 3, 4, up to 7. So to convert a decimal number to an octal number, we perform repeated divisions again, just like we did with the binary number. But this time around, we are no longer dividing by 2. We are dividing by 8 because we want to convert the number to the base 8. So we are now dividing by 8. So for instance, let's suppose we have the number 78, which is to base 10, and we want to convert it to base 8. What we will do is we divide 78 by 8, we get 9, remainder 6. Next, we are now dividing 9 by 8, we get 1, remainder 1. Next, we divide 1 by 8, we get 0, remainder 1. And we now take our remainders from bottom to top. So that means 78 to the base 10 will be equal to 116 to the base 8. As simple as that. We can also convert an octal number to a decimal number. The concept again is the same as what we did when we were converting binary numbers to decimal numbers. What is only different is that our place values are now 8 to the power of something, not 2 to the power of something. So the place value of this one is 8 to the power of 0, 8 to the power of 1, and 8 to the power of 2. Now we are going to multiply this place value by the digit that it corresponds to. So here we have 8 to the power of 0, that's 1. 1 times 6 will give you 6. 8 to the power of 1, that's 8 times 1, that will give you 8. 8 squared, that's 64 times 1, that will give you 64. Next, we add these numbers and we get 78. So that means this number 116 to base 8 is equivalent to 78 to base 10. Okay. So we can see that here, this number 78 to base 10 is equivalent to 116 to base 8. Now, your task is to go and find out how do we convert an octal number to binary and how do we convert a binary number to octal. That's your homework, and we are done for now. Thank you.